about the program. As you know, and you can see, we have a very tight, condensed, long program with no free time to breathe. That's good. Unfortunately, this leaves us only little time for questions and discussion during or right after the talk, so the times you see on the program include a couple of minutes of questions, but at the end of the session, in the morning and in the afternoon, we do expect to have a longer discussion session, and of course, we have the breaks where we can all discuss things. With any issue that has to do with the program, either talk to me or to Colin, raise your hand, who is the real master of all the great details of the program. As for putting the lectures on the web, John, who is collecting? Okay. You see that Martin is already got a good grade for his behavior because he put his, no? It's just a test. Okay, sorry. You don't deserve the grade. Okay, pretend that Martin did it, and you see that's how it looks when after you put your lecture on. So please do. We really want to collect all the lectures so people can really interact also with the lectures. Do you have any announcement tonight?
Is there an email that they can send the lectures to? I'll put them on USB. Okay, so see, why don't you stand up in front? Move out in front so people can see you. Okay, so this is C. Go, who's actually a student from Columbia University who's here this summer working with us. So he'll be responsible for collecting the slides. And I'll see if we also can set up an email account where you can mail them if you want to. But otherwise, just on the... TZGOH at ucsc.edu.
Okay, then we'll get started. As I understand it, our third speaker is not available this morning, so we'll have a little bit more time for questions before the coffee break. Without further ado, I will introduce Martin Haehnelt, who will be talking about probing reionization with Lyman-alpha and 21 centimeter experiments. So.
Okay, it's a pleasure to be back here, and I very much appreciate that you have scheduled me early in the morning when I'm still awake. So I will tell you about what I and the people I'm working with have done lately in terms of probing reionization. And before starting this, I think I should mention the long list of people I'm working with. I've highlighted in blue 4 grad students, 3 of which are finishing this year. So don't worry, they all have jobs, so I'm not pleading for you to hire them. And the last one has just started, but they have done sort of a lot of the work I will be showing here. What you see on the first slide is one of our simulations of how reionization actually proceeds, and you will see more of this later on. I think I will not spend much time on the introduction. This is a very nice slide that Brand Robertson has compiled some years back that's shown in these talks routinely, and I think Brand is here in Santa Cruz now. And sort of, as you know, sort of we are trying to push back beyond redshift 6 into a regime where we sort of study the phase transition where hydrogen goes from being neutral to being ionized by the first galaxies and CMBs, by the first galaxies and black holes. And there are sort of 4 main probes with which we want to study this. The one is the CMB, who sort of eliminates that from behind. And then there's Lyman-alpha absorption and emission, and 21 centimeter absorption emission. I will touch on all of these briefly. I think first, to get the CMB out of the way, I think the main thing with the CMB tests is the electron density integrated that's termed in the Thomson optical depths, and the value that has been inferred from the CMB values has come down with the years, and smaller values basically mean later reionization. But overall, what you have to keep in mind is when the CMB puts out the measurement of the electron optical depths, that these are still 1 sigma error bars. So I think in terms of the CMBs, the constraints are still very weak. So apart from very early reionization, I think everything still goes. What I will then later discuss is sort of a range of reionization histories that here shown in 3 colors, and show how we constrain these. One corresponds to the Hardeman 2012 model, what's sort of a benchmark in the field. And I will try to convince you that we meanwhile think that things might sort of happen in bulk a little bit later. This is sort of how the volume filling factor for these three models look. So sort of half the volume filled by ionization varies between sort of 7 and maybe 10 in these models. And the fiducial model that I will sort of advocate that fits most of the data is what's shown here in red, where it starts sort of at about 13 or so, and has reached midway, maybe a little bit before redshift 8. So what we want to find out is how early does it start, how late does it finish, and actually what are the ionizing sources that do it. So first, a little bit about Lyman-alpha emission from high redshift galaxies. So why is that a good probe? The reason being that galaxies don't only emit continuum emission, but they, depending on what their properties, have a strong Lyman-alpha line as well. Lyman-alpha is very sensitive to neutral hydrogen and can easily be scattered out of the line of sight. So if the universe becomes progressively neutral as you go backwards in time, this is sort of a sign that the Lyman-alpha should disappear before the continuum emission of the galaxies disappear. This seems to be the case. So sort of if people look actually at Lyman-alpha selected galaxy, the luminosity function seems to drop very quickly. And if you look at the Lyman-alpha strength of continuum selected galaxies, you see a similar thing. We have tried to sort of model this amongst other people. This is sort of challenging to model because you A, need large scales to sort of model the whole galaxy survey, and B, you have to get to the small scale physics within the galaxies, as well as to the small scale physics of what actually are the things of the ionizing radiation and that scatter the Lyman-alpha as well. And for this, you need both basically large volumes and high resolution. And in this particular work, we have sort of taken a hybrid approach, taking a large box and tiled this with many small, high-resolution hydro simulations. And we're actually to reproduce these evolution of the equivalent widths that you see in high redshift galaxies very well. If we assume sort of the latest of these reionization histories that I've shown you, that's shown here in dash. So this is the equivalent distribution of galaxies as it evolves as you go to higher redshift, the 6, 7, and 8, and this evolves very rapidly. And if we sort of take the latest of the ionization histories that I've just shown you, this sort of fits the data reasonably well. So the rapid decline of the Lyman-alpha emission at redshift 6 requires a significant decline of the volume-weighted ionized fraction. And this is sort of not trivial to achieve in sort of a model, for example, like Hadamard-Dow. Reionization really seems to sort of finish a little bit later. So sort of now I want to review a little bit what you see in Lyman-alpha absorption. And what you do there is you take advantage that you can look at very bright objects and then look at the absorption of the Lyman in the spectra. This is sort of still the current record holder, even so sort of there are rumors that there's a higher redshift quasar now. Yes. So this is a redshift 7 quasar, this for which we have now a very nice X-shooter spectrum, 30 hours, and 2 new papers out. Bosman et al. Who looked at the metal absorption, and Barn et al. Where I'm not part of, where we looked at transmission spikes, where we'll show you some modeling. So the quasar looks like a normal quasar at lower redshifts, but here you see sort of the effect of the universe becoming denser and more neutral. So you see a very long absorption troughs, and here a few spikes. This is high resolution that I will discuss in a little bit more detail later. What was remarkable about this quasar is that it seemed to have a very short, what's called a near zone, that's ionized by the quasar itself, and maybe a red damping wing. And we have sort of modeled that over the years. The latest attempt by Laura Keating, my grad student, who is now moving to CETA. And initially we thought that's a good way of probing how neutral the gas is around the quasars. In the end, it turns out that it's quite degenerate with the lifetime of the quasar. So you can model both the red damping wing and the size of the near zones quite well, but the constraints in the end never get too strong. The additional problem is that becomes increasingly clear is that you need to know the intrinsic spectrum of the quasar very well. And there might actually be quasars that might mimic as if they're sitting in a neutral environment. And there was a nice thesis by a student of Joey Eilers, where she basically showed that some lower redshift objects have very short near zones as well, even so they're obviously not sitting still in a neutral environment. And so sort of this was a little bit disappointing in the end, that this is a measure of the neutral gas might not work that well. What the newest thing is that there's allegedly now a redshift 7.5 quasar. We haven't seen a spectrum of where people heavily involved in modeling it, that hopefully comes out soon. So there will be soon news on this. So the next couple of minutes I will talk a bit about our own radiative transfer simulations, where we sort of model these processes of the universe getting more ionized in detail. So these are simulations where we have taken a Ramsey simulation, hyper simulation, underlying simulation, and post-process with a radiative transfer code, and then very carefully try to reproduce the absorption properties of the Lyman-alpha forest in high redshift quasars. So this is sort of our best bet of the timing of reionization. The first sources may be appearing at redshift 13 or so. If you go to a larger box, maybe even a bit earlier, completed by redshift maybe 6, and a few island of neutral gas still there, a little bit above redshift 6. Sort of we have looked at this to reproduce sort of the properties of the Lyman-alpha force with this, and lately we looked in these particular transmission spikes that I will discuss in a little bit more detail in a few slides just now. So this is a spectrum of the redshift 7 quasar, and in this case it's a simulated spectrum, and you see there's a very long trough all the way from redshift of the quasar down to a redshift of 6.1, where there's basically no emission whatsoever. And in the observed spectrum, you find then 7 spikes just in this little bit of redshift range here. And it just turns out that our fiducial reionization history reproduces this extremely well. So this is sort of the 7 spikes in the observed spectrum, or 5 of them. This is a couple of them in some of the redshift range here for our simulated spectrum, and we really reproduce these very well. And if you look statistically, sort of how sensitive it is when actually reionization finishes, and there's a technical term for this when the H2 regions overlap, that's called percolation. And this very tiny redshift range that's shown here by the 2 vertical lines, gamma changes very quickly, and this sort of exactly happens at this redshift here. So you go from having a few transmission spikes to having none. And if you look at the number of spikes that you see for these very closely set reionization histories that are very similar actually indeed, even these small differences when gamma rises leads to a large difference in the number of spikes you would find in this redshift range. And we find that our fiducial model actually fits that very well. It's a little bit dependent on the temperature of the gas that you assume, but this is a very sensitive probe for when percolation actually happens. So the onset of the transmission spikes is really very, very sensitive to when exactly reionization finishes. So what does it tell us in terms of, for example, the Haehnelt 2012 model, sort of what the emissivity of ionizing photons actually is? This is 2 of these reionization histories that I have just shown here that fits the photonization rate that you infer from the Lyman-alpha forest very well. And this is the corresponding ionizing emissivities, and black is what you have in Haehnelt. And you see that you need a slightly different redshift dependence. Sort of the overall offset here is just due to the fact that depends on the resolution, how many photons you need to actually get out of the galaxy, but the redshift evolution is slightly different. So the rapid rise in Haehnelt at the quasars at redshift 3 sort of is not consistent with what you need to actually the flat evolution of the photonization rate here. Sort of, so I've shown you now what works well. What doesn't work so well in these simulations is actually to get the relatively large opacity fluctuations that you see on very large scales. So this is a point that George Becker always likes to make. This is 2 quasar spectra here, and one of them for the Lyman-alpha forest between the redshift 5.5 to 5.9 has a very long trough that corresponds to 160 megaparsec co-moving, while the other one has lots of these transmission spikes. And those of you who work in large-scale structures, they know that at this redshift, 160 megaparsec is a very, very large scale. So the density fluctuations on 160 megaparsec scales are actually tiny. So how can the universe be so different in one place and another place sort of where there seems to be all absorption? This is sort of a puzzle where we have been working on the last 2 or 3 years, quite a few other people too. One suggestion how to explain this is sort of that the temperature is quite different on different scales, depending on when exactly ionization happens. So the idea is that the recombination coefficient is temperature dependent. And then if I sort of ionize, I get to a high temperature, and then I drop mainly due to component adiabatic cooling. And if I extended radiation with a wide spread of ionization redshift, this should lead to large opacity fluctuations. I had Lo in her last thesis paper look at this. So we did detailed simulations. If you actually do these ionization simulations and try to do the temperature carefully, and indeed you get these temperature fluctuations, but maybe not quite on this large scale. So this is here a 20 megaparsec box. And if I show you here when the different patches of the universe were reionized, and you see it's the hot regions that are indeed the ones that have been ionized latest. So the ones that have been latest are still hottest and didn't have time to cool. So this whole region is still hot. But if we looked into if that can explain the large opacity fluctuations due to the temperature dependence of the recombination coefficients, it just doesn't work. It's not a large enough effect. What we had instead suggested, what might actually do it, is that you have actually large fluctuations in the photoionization rate. And if you want to do that over 100 of megaparsec scales, I think the only thing what probably could reasonably do that would be QSOs. And this goes together with, I had just explained you that this rapid evolution of the QSOs as you go to higher redshift, this rapid decrease, sort of not quite consistent with what you see in the evolution of the photoionization rate. So we have explored the possibility that there are a few more quasars than people believed, and that went into the Harder-Maddow model at higher redshift, and there's some observational evidence for this as well. So if you model this and take a large box and just look at the emissions that the quasars do, you get basically the transverse proximity effect everywhere in the spectra, and you get large opacity fluctuations. And this is sort of a way of getting these spectra where you have with a very long trough over here 160 megaparsec or 110 megaparsec H inverse, and the other ones where you basically still have lots of transmission spikes. So if you do this, you get actually a distribution of the effective optical depth in the spectra as observed. But it obviously has a downside that you assume quasars that are stipulated, and sort of observers still have to find. So if that's really a solution, I'm sort of oscillating on for a while. That was the only thing what I think would work. I think we're working now a bit harder to look into the third model that has been suggested, and that the large mean free path fluctuations on these large scales. And perhaps this is a way to make this work in case these quasars actually not found. He's just giving me the 5-minute sign. So the remaining time I want to sort of present the work where we've looked a bit closer into the galaxies that actually produce the ionizing radiation. So this is similar simulation here as sort of the universe becomes more ionized as individual H2 regions overlap. But this is now done with the Ramses RT. And this uses now the adaptive mesh refinement of the code to actually look at the individual ionizing galaxies, to sort of prepare a bit for JWST and to interpret ALMA observations to actually zoom into these galaxies and see how the photons actually climb out of these galaxies. It's quite amazing that you can do this in this detail. So you can now do a full ionization simulation with sort of live sources, where you actually have individual star-forming regions that lead to large fluctuations of the photoionization rate within the galaxy, including feedback in the galaxy, modeling the young, the intermediate, and the old stars separately, looking at the distribution of neutral and ionized hydrogen. And this you can, for example, use, and this is work of my student Harley Katz, who is moving to Oxford in fall. And what he has tried to model here is sort of to look at these kind of ALMA observations, where people found that if you look at the C2 and oxygen 3 emission, this can be actually quite offset from both the Lyman-alpha emission and from each other. We have these large offsets in the different lines. And to our surprise, when we looked at our galaxies in this epoch, you actually find a very similar thing. You find actually very strong offsets between C2 and oxygen 3, and the main reason being here is that the oxygen 3 is actually collisionally ionized due to feedback heated gas, and that is slightly offset from the C2 that sits in the nodal region where actually the gas sits. So somewhat counterintuitively, you actually get these offsets with star-forming regions that where the feedback heated gas produces option 3. And sort of normally people think option 3 is a sign of AGN. So we did model this as well and put a little AGN in these simulations. And the funny thing is if you actually put the AGN in, these offsets disappear. The reason for this is that now the diffuse option 3, this is collisionally ionized, becomes ionized to higher ionization states. And the only option 3 you get is from the denser regions that you ionize with the AGN, as in the classical picture where option 3 is sort of produced by AGN. But then the offset disappears, and the C2 and the option 3 actually come from, say, spatially the same region. 2 minutes. So the last 2 minutes, I will briefly talk about the work we have done on 21 centimeter emission and absorption. So for this, we have sort of, this is sort of looking a bit forward. I think this is the main science case of SKA and of instruments like LOFA and HERA that a bit earlier, is to actually look at 21 centimeter emission and absorption. And as we are quite confident that we have sort of very well calibrated our reionization histories, with the current data at low redshift, we basically have made predictions for what happens if you interpolate that backwards too, and have actually reionization history that is sort of consistent with all the low redshift data. So these are some of the models that I have sort of discussed before. This is our fiducial model that I've discussed quite a lot. Galaxies and sort of late, but not very late. This is a very late model that's maybe favored by the rapid disappearance of the Lyman-alpha emitters. And here we have done a model where the sources actually are exclusively QSOs. And what you see if you basically put QSOs as sources of reionization, your individual patches become larger. And if you look in the power spectrum, what that does nicely is in the 21 centimeter power spectrum, that raises the signal quite a bit. So the colored models here are all models where the reionization is driven by AGN. I don't believe that this is actually the case, but this is sort of a very nice model that might be firstly ruled out by the data. And with a model like this, you actually sort of already, within a factor of few, with the paper results. And HERA and perhaps LOFA should get there easily. And this AGN-driven models with the large bubbles, they should be the first models they should be able to rule out. And they should finally get to these galaxy-driven models down here. So before advocated QSOs might drive large opacity fluctuations. But I think even if that's the case, they're probably not driving reionization. They're just taking over in sort of the ionizing emissivity slightly after reionization. Sort of, he's just showing me the last minute sign, so to just sum up. So I try to convince you sort of that there is evidence building from a whole range of observational probes that reionization actually happens rather late, that we sort of, the sum was misled by the early WMAP result that sort of pushed the modelers into very early reionization due to spuriously large electron optical depths. I explained to you that sort of while we by and large can model the Lyman-alpha absorption very well, there's still a problem that's a broad flux PDF that suddenly broadens at redshift 5.6 that may require substantial contribution of QSO. So it might be interesting to sort of really push the surveys for what I would call L-star QSOs at higher redshifts. And the modeling of the mean free path fluctuation, what would probably be the remaining alternative model, this is very difficult because you really need to do the same simulations well calibrated with a very high dynamic range, basically larger box. And we're working on this, but this will sort of keep us busy at least for another year or two. And I showed you a little bit about the predictions for SKA, how these models that are calibrated at low redshift look in terms of 21 centimeter power spectra. And if this were 20 minutes, I think I want to stop here. Now, I showed you two kinds of simulations. I showed you the ones where we basically where we calibrated to get the Lyman-alpha forest right. So there we basically just played with emissivity till we got percolation at the redshift where it happens. So we started off with a Haehnelt emissivity, and then we just adjusted it a little bit up. And this is sort of not converged, because as you sort of increase the resolution, there will be more photons absorbed in the actual galaxies where the photons are coming out. So this was sort of enforcing a reionization history to see what is consistent with the Lyman-alpha forest. In the simulation that I showed you later, this is sort of the other approach. You basically run your simulations and you basically try to calculate the escape a priori. And this is a much harder problem. And then you sort of have to take, when reionization happens in your simulations, more or less as it comes. And this is very hard to calibrate, and you end up then with a reionization that might happen at 4, 8, as many have been published. And to sort of, to really get to merge these two approaches, we're working now together by probably adjusting the escape fractions. But we have sort of not assumed an escape fraction, we've assumed an emissivity till we got a reionization history that's consistent with the data.
In Michael Coulin's dissertation research with Pierre Amadou, where they put in significant reionization from quasars, the basic structure of the reionizing region was different. Instead of Stromgren spheres, you have much larger regions, but only partially ionized, and the ionization is mostly from knock-on electrons. Is there any evidence that supports that, since you're invoking maybe extra early quasars? Are there ways that we could tell if that's what's really going on?
We only have the good data after reionization is finished, and there you wouldn't see the difference. And before, this is sort of the effects you eventually may be looking at if SKA works very well. But there's no observational evidence for that whatsoever. And I think...
So studying the structure of the ionized
But
regions.
I think sort of really doing reionization with quasars, I think this will probably be very hard, because quasars sort of favor the more massive halos, and at some stage they die
But your
out.
picture is galaxies, but maybe extra quasars needed to really...
So all I wanted was basically the quasars to disappear a bit later.
Right.
So instead of disappearing here, to push that to redshift 5. But the galaxy is still taking over in the epoch. All what we're looking at is sort of up to redshift 6, where the universe is fully ionized, where we wouldn't see an effect like this. So the individual regions, we would have to go to redshift at least 7, probably 8, and there we don't have the data.
In the old days, before high-quality simulations like yours, people argued whether reionization occurs first in low-density regions, where there isn't that much gas to ionize, or in high-density regions, which is where most of the initial photons are going to come from. Roughly speaking, how does it look based on the best models now?
Now, this is sort of a discussion that sort of has been a bit misleading. I think the photons will always be produced in the dense region. And the sources are biased too, so it goes from the dense region outwards. But the late stages of reionization will always be outside in. Because as you know, in the low redshift universe, the only neutral gas is in dense region as well. So there's a transition from sort of going outside, from inside out to outside in. After percolation, it's going into the dense regions, and before, it's sort of going out of the dense regions. I think there was actually sort of never a suggestion that you start reionization where you have no sources.
Time for maybe one more question. I'll ask. I'm curious about the ALMA Lyman-alpha offset that you have. If you just include the star-forming regions, are you capable of ionizing the oxygen-3? Do the models reproduce that?
Yeah, I think quantitatively we don't know. What's shown here is just sort of column density. We haven't tried to really model the emission, because this is really difficult. But you get the oxygen 3 in the first place, and as I said, what happens is where you have the oxygen 3 here, is this is actually supernova heated gas that flows out of the star-forming region that's collisionally ionized. And you get a nice peak with this too. If that would work over a large sample, if you have enough oxygen 3 as often as you see in the galaxies, this is a different question. This is sort of, but qualitatively it works very nicely, and there it's collisionally ionized. The rest will be a bit harder to really do that qualitatively, but this is sort of what we will see over the next 5 years or so, that people try to do that more and more.
That's a good prediction to go look for. Okay, let's thank Martin again. And we will welcome our next speaker, Steve Finkelstein, who will also be continuing the discussion on reionization.